Hey everyone, welcome back, and today let's solve Leetcode problem 2558 titled Take Gifts from the Richest Pile. So we're given an integer array gifts denoting that the number of gifts are in various piles. And every second we can do the following. We can choose the pile with the maximum number of gifts, and if there is more than one pile with that value maximum number of gifts, we have the choice to choose any of them. And once we've actually chosen that, we have to leave behind or replace that value with the floor of the square root of the number of gifts in that corresponding pile and take the rests of the gifts. And we need to return the number of gifts remaining after k seconds, or in other words, after k operations. So in example 1, we have our input array gifts to be 25, 64, 94, and 100. These are just simply our different piles of gifts and their corresponding richness or wealth. Really, we just care about their values of how large or small they really are. And our k value to be 4. So in other words, we have to return the total number of gifts remaining after 4 seconds, or rather after 4 operations. Well, in the first operation, we notice here that the largest element, or the richest pile, is 100. So we're going to replace 100 with the floor of the square root. Well, the floor of the square root of 100 is simply just root 10, or rather root 100, which is equal to 10. And so this 100 then becomes a 10. Once we replace this 100 with a 10, we see that the next biggest element is going to be the 64. So we take the 64, we actually floor its square root, we get 8. And then after that, our next biggest element is 25, and so on and so forth, until we've actually completed 4 operations, or rather, we've actually done 4 seconds of operations, and we just need to return the number of remaining gifts after we do all of these operations. And that would be 5, 8, 9, 4, and 3. And so to get the total number of gifts remaining after these k operations, we really just have to return the sum of our remaining data structure, right, after we're done with these operations, right, because that's going to tell us the sum of the total number of remaining elements we have and the remaining values after the operations in our input array gifts. So for example 2, we have our input array gifts to be just 4 ones, and our k value to be 1. So the reason why is because, well, really all of these guys are both the smallest and largest values, right? And k is equal to 4. We have 4 elements as well. And regardless which pile we choose, we're going to get a result of 1. Because no matter what we do, the floor of the square root of 1 is simply just 1. And so we're never going to have a pile with a richness other than 1. So regardless what this k value was, even if it was like a million, we would still have 4 ones. Because we can't change this 1 to be any other value, because the moment we floor the square root of 1, we still keep 1. We're not actually changing the value to any other operation or value, regardless of what k is, regardless of how many seconds we actually do this for, right? We're going to have to leave behind exactly 1 gift in each pile every single second, regardless of which pile we actually choose to change or replace. And so the total number of gifts remaining are just going to be the original sum of this input array gifts, because of course all of them are 1s, and in this case that's just going to be 4. So technically you could have a base case for this, but you shouldn't need to address this. It's really redundant, and I'll show you guys why that is in the code as well. But yeah, that's simply just a quick thing that you can take away from this example. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to actually solve this problem the most efficiently, we're actually going to be using a data structure called the max heap. So in Python, the language that I'm going to be using for this video, the max heap isn't actually directly built in to Python, but there is a quick workaround we can do, because the reality is we actually do have the minimum heap or the min heap priority queue built in Python, and we can actually use that to our advantage and kind of just use it as a max heap using our negative knowledge. So I'll show you guys how that works, but before we actually dive into how that works, let me actually explain the kind of a quick rundown of how our algorithm and how we actually use it to implement our min, or rather max heap data structure. So First of all, we want to just push all the piles into that max heap that we just talked about. And the reason why is because we want to easily retrieve the maximum number of gifts, right? In other words, we want to easily, efficiently retrieve at the top of our priority queue or max heap, basically the pile with the largest value, the most rich gift at that iteration, rather the most gift pile at that iteration, right? And we can do this actually in log n time. And of course, we love logarithmic operations and algorithms because they're really almost just about as efficient and fast as you can get, similar to binary search, right? And that's exactly the time complexity for popping and pushing onto min and max heaps. In this case, we're using a max heap to get the largest value rather than the minimum value, right? And once we actually retrieve the pile with the maximum number of gifts or the maximum value for each of the k operations, right? For each of them, hint, hint, for our parameter k, we're simply going to pop the largest element, right? In other words, the richest pile at that iteration from our max heap, and then compute its actual floor of its square root. And once we actually compute that result, we want to just push it back, rather push the updated value back into the heap and use that for future computations in future iterations, right? And after we actually perform all the operations, like I was talking about before, we simply have to sum up all the remaining piles in the heap, right after we're done with all the operations, and simply just return that as our final answer, because that's going to give us the remaining number of gifts remaining after t seconds. It's simply just the sum of all the different gifts and all the different remaining piles after we finish all k operations in our max heap data structure. So, with that out of the way, let's go ahead and dive straight into the code here. So, I'm actually going to do something that I usually do in my videos, import two modules that we actually would need if this wasn't Leetcode for the code editor, right? If we were in like VS Code or some IDE like that. So I'm going to import heapq, and I'm also going to import the math module. So again, these are already pre-imported and pre-installed into the Leetcode code editor the moment you actually start using the website. So it isn't actually necessary to use or import any external modules, but I just like to do this for best practice because it really helps me understand which modules I'm actually using and how it actually is incorporated within my code, right? But feel free to just ignore that if you would like. But once we actually import these two modules, now let's actually start working on the main code here. So I'm first going to initialize my max heap, right? So I'm going to set max heap to be equal to, in this case, like I talked about before, we only have min heaps built in directly into the Python library. We don't have direct access to a max heap, and this is where we have to actually be kind of clever. Instead of just implementing or rather integrating every single gift in the max heap to create a min heap, we want to rather increment or rather update our negative gift for every gift in our input array gifts, right? And the reason why I'm choosing the negative gift is because instead of making this max heap a min heap data structure, we'd actually be able to actually heapify this in Python to be a max heap data structure. And the reason why is because think about it. When we have two values, 1 and 2, well, in this case for our min heap, 1 would be at the top of the heap, the original first value or initial value that we would actually pop out. The reason why is because, of course, it would be a min heap, and 1 is smaller than 2. But if we take the negative of these two values, we see that -2 is then smaller than -1, right? So, in other words, -2 would then be at the top of our heap data structure. And notice how 2 actually has the larger absolute value. And the only reason why we're putting this at the top of our data structure is because it's a min heap by default in Python. So this is going to be a negative value. So -2 is of course smaller than -1. But we can actually just take the negative or the absolute value when we actually pop from our max heap and use that value to compute our actual corresponding floor of the square root. That's one clever way to actually get the max heap data structure using negative values in Python, because of course the min heap is kind of the default, right? So we're basically implementing every single negative pile or negative gift for every gift in our input array gifts, right? This is also known as list comprehension here in Python. So once we've done this, now we want to actually turn our max heap into an actual max heap, right? Right now it's still just a regular array, and the way we can do that in Python is simply just use heapq module and heapify. So .heapq.heapify, and for our parameter, it's the data structure or the heap that we're actually trying to make a heap, right, that we're actually trying to heapify. And in this case, that parameter is simply just our max heap, which we defined up above. We're simply just creating this max heap and changing that to be an actual heap data structure, so we can actually get the largest values in log n efficient time. Now let's actually loop through our k value, right? Now let's actually implement these operations k number of times using a for loop. So I'm not actually going to use my iterator here, so I'm just going to use an underscore for my placeholder for my iterator. So in the range of k, simply just saying that we're going to do this k seconds or k operations as the problem tells us, right? That's literally the definition of k. Let's actually get our squared max value, right? Let's actually get the floor of the square root of the number, right? The maximum value. So for every basically iteration in the range of k seconds or k operations, we want to get our squared max value. So squared max, and it's simply going to be the math dot is square root, and you can translate this in Python if you want. All right, I think it's is square root here is how it's probably in Python. Might have to double check that. And the way we're going to do this is actually negative heap q dot heap hop from our data structure. In this case, that data structure is our max heap, right? And again, we could also take the absolute value, but just for some extra readability here and simplicity for my code as well, I'm going to take the negative. We discussed before that -1 and -2, in these two values, -2 would be at the top of the heap, because by default, when we're actually taking the heapifying our heap data structure, it's going to be turned into a min heap in Python. And so when we actually pop and take the negative of the smallest, in term, quote, smallest value in our maximum heap, we're turning this -2 to be a 2. So all of a sudden, we're simply just taking the absolute value and actually getting its true largest value from -2 to 2. We're removing the negative that we actually added onto the max heap to actually make it have a truly max heap operation value. So -2 would then become 2. And notice how 2 is actually the largest value in these series of values. Of course, if we had more values, it would be more realistic. But this is just a quick kind of simulation of what would actually be happening when we actually access and pop from our max heap data structure. So once we actually got the squared max, then we want to actually pop, or rather push it onto our heap queue. So we're pushing to heap queue.heap push. The first parameter is going to be the data structure that we're pushing onto. In this case, that's still the max heap. That's the only actual data structure that we're using for this problem here. And we're going to push onto it the negative squared max. Again, we still have to keep our negative value because we still want this to be a max heap, and we're just going to use this negative value for future computations for future iterations, right? And once we're actually done computing this in the range of k, after k seconds or k operations, we simply want to return the negative sum of the max heap, right? And the reason why, again, it's negative is because we don't want a negative sum, we want a positive sum, and we just take the sum of all the different elements or piles at our max heap and just take the absolute value or the negative of that result, because that would then convert it to a positive result. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. And as you can see, this is just about as efficient as you can get, right? It's going to have a runtime complexity of, actually, before we get into that, just notice how it actually beats 100% of users, and it really just is about as efficient as you can get memory-wise as well. It takes 17 megabytes of memory, and really, it says that I take 0 milliseconds to actually run this as well. Okay, and I beat 100% of users. Okay, so effectively, for a quick high-level rundown, how are we actually kind of solving this problem using this max heap knowledge here? Well, we're simply just repeatedly reducing the richest pile's gift count, right? And we're just reducing it down in the squared max variable to its integer floor square root. And we're doing this in the range of k. So effectively, after performing k operations, we're going to compute the total number of gifts left. And by using this max heap data structure, right, we're simply just making sure that for every operation, we're going to actually pop off in log n time from our max heap the richest pile, or rather, in other words, the pile with the largest value, right? So it's done most efficiently, calculating then its floor square root and adding it back as a result to our heap queue, its negative values, to actually maintain the order and the values of the max heap rather than the min heap. If we actually push the positive value, then it would actually become a min heap. We want to actually get the negative value. So for the time complexity here, let me actually comment this out for you guys as well. The time complexity, okay, I was going to put runtime, doesn't really matter. Those two vocab terms are interchangeable. The time complexity is going to be big O, of n plus k log n. Okay, let me actually put this n in parentheses as well. Right? Oops, I think okay, that works. Okay, so the time complexity is going to be big O of n plus k log n. And let's just kind of break this down to see how we actually got this kind of advanced, kind of complex runtime complexity. Well, to actually initialize our heap, to build the max heap, that's going to be a linear time operation, right? It's going to be a big O of n operation. What is n? It's simply just the length of our input array gifts. It's simply just the number of piles, the length of this gift's input array. Right? That's going to be a big O of n operation to actually, again, initialize or build this heap, right? And then for actually our heap operations, each heap pop that we see over here, heap pop, and each heap push, that's actually going to be a big O of log n operation, right? Like we discussed before. It's still very efficient, don't get me wrong. Log n is a very efficient runtime complexity, right? And since we actually perform, notice how we're actually performing this heap pop and heap push operation exactly k times, because we're doing this in the range of k. We're doing this exactly k times, right? Because that's literally how k, the input parameter, is actually defined to be, right? And since we're doing this k times, this part of the algorithm is going to be big O of k log n, and this part is going to be big O of n. So the final time complexity is going to be that big O of n to actually initialize or build our heap plus the k log n to actually pop and push onto our min heap and from our min heap, or rather max heap, k times. All right, so that's going to be the final runtime complexity. And for the space complexity, let me also comment this out here, space complexity. This is going to be also pretty simple here, big O of n. I don't know why I said also. This was not really simple, but this is pretty simple. It's just really big O of n, right? Because again, really, we only have one extra data structure here, one extra data structure of auxiliary memory. It's going to be this heap, of course, right? This max heap, where we literally store all the different elements from our input array gifts. And again, n is going to be the length of our input array gifts. And so for this extra data structure here for the max heap, that's going to be the main storage, right, of the heap. That's going to be a big O of n, or linear time memory complexity operation. So that's going to be it for today's video. If you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.